All right, here's an example of a diagram showing simple harmonic motion. This could be a spring bouncing up and down or a pendulum swinging back and forth. We see here in the middle of the graph, this is graphed vertically. In the middle of the graph, I have zero displacement. And then over to the right, I have a positive x displacement, and over to the left, I have negative x displacement. So this would be a good diagram for a pendulum. As it swings to the right, it displaces in the positive x direction, and then as it swings back to the left, it displaces in the negative x direction. And these little red arrows here, these are the velocity vectors. As a pendulum swings, it has its greatest velocity in the center of the swing, and then as it swings closer to the maximum displacement to the right, it slows its velocity until the velocity at the end of the swing, or the furthest displacement, is zero, and that's where it is briefly a velocity of zero, and it turns around and starts coming back the other way. So we see our velocity vectors now point to the left because the pendulum is swinging to the left, and the velocity is increasing. The magnitude of the vectors is getting larger until at the center point again, the velocity is greatest, and then it slows down again as it gets to the farthest negative x displacement. The velocity is zero once more, and then it speeds up back toward the center and slows down as it reaches the positive x max displacement. So here's a graph showing if I choose to start at this point right here, I would have a maximum positive x max displacement, and it goes to zero and then to the negative x max and back to zero and to the positive x max and so on. It's swinging back and forth between positive x max and negative x max. So this is a graph of its displacement as a function of time. Okay? Let's go over some of the vocabulary associated with this. How many times does the pendulum swing per second? How many oscillations per second? We call that the frequency of the oscillation, and we give it a unit of hertz, abbreviated Hz. So 10 hertz would be something that vibrated or went back and forth 10 times every second. The period is the time it takes for one complete oscillation. And we see that the relationship between the period and the frequency is that they are reciprocals of one another. In other words, taking the example of a frequency of 10 hertz, if something vibrates or oscillates 10 times per second, then each vibration or each oscillation will be 1/10 of a second. There's 10 oscillations in a second, so each of them is 1/10 of a second. If there were 5 oscillations in 1 second, then each oscillation would take 1/5 of a second, and so on. So the relationship is the frequency and the period are reciprocals of one another. Let's look at some examples. Okay, so I clicked down in the lower left corner where it said animation here, and it took me to this website, this YouTube page, and let me enlarge it here. This is a little movie, or a little animation, showing a spring oscillating and the displacement, the velocity, and the acceleration as a function of time as it's happening. So you can see at the endpoints of the oscillation, let me start it over here. At the endpoints of the oscillation, I have maximum displacement at the top and at the bottom. This graph shows me how the velocity varies throughout the oscillation, and this graph shows how the acceleration varies throughout the oscillation. And I'm going to start it over again. Notice that the acceleration is maximum when the displacement is maximum, and the velocity is zero at the maximum displacement, and maximum velocity at the what's called the equilibrium point, or the midpoint of the oscillation. I've clicked now on the movie link in my PowerPoint slide, and it's taken me to this YouTube video. called spray paint oscillator, and it's going to show us an oscillating spring that has a paint can attached to it. So basically what they're going to do is let this can of spray paint oscillate up and down while they move the paper behind it past it. And you see the result is a sine wave. All right, here's the next slide in the presentation. These three diagrams show comparisons of two different oscillations. The first one, we have different amplitudes only. So you can see here how far the oscillation displaces from the zero or the equilibrium point is different. So we say that the amplitude of the oscillation is different for these two. The amplitude being the displacement from the equilibrium point or the center point. In figure B, we have different periods. Period, remember, is the time of the oscillation. So you can see here for the blue oscillation, the time it takes for one oscillation is twice that of the red curve. The red curve oscillates twice within the same time period, and the red oscillation only occurs once. So these two waves have different periods. And then in the third one, the phase is different. So you see the amplitudes of the wave is the same. The period is the same, the amount of time it takes for an oscillation to occur. But the phase is just where we decide to start looking at the oscillation. So here at time t equals 0, we look at the blue wave at its maximum displacement, but with the red wave, we start time equals 0 when the oscillation is in this portion of its oscillation. And so we can compare the two. Don't worry about this phase angle, it's called. We're going to go over that in the next slide. So let's take a look at an example. If you want to try this out yourself, you can try this at this website here. Okay, so I clicked on the link on my PowerPoint slide where it said try it, and it takes me to this website, and here is an oscillation, a graph of an oscillation, and it's going to allow me to vary the amplitude, the period or the frequency, and the phase. So here's the form of the equation for a sine wave, where A is the amplitude, the maximum amplitude, and then times the sine as it moves through time. We're going to talk more about this later in the lesson, okay? But this just lets you try it. How does my wave change when I change the amplitude of the wave? So I'm going to use this slider, and I'm just going to move it to make the amplitude more or less, and you can see that the blue wave is the one I'm changing, of course, and the red wave is the reference, what it was before I changed it. So there's changing the amplitude. Here, I will change the frequency of the wave. And so you can see by changing that number, that changes the frequency, or how, which also means changing the period. And then the phase, right here, as I change the phase, you can see it moves from left to right, or right to left horizontally. That's changing the phase. So you can experiment with this, and as you become more familiar with the equation, you can use this to check your understanding. All right, here's the next slide of our presentation. This is relating the angular frequency, which we represent with the letter omega, to the oscillatory frequency, F. So the oscillatory frequency is what we were talking about earlier, that it's the number of oscillations in a unit of time. So 10 hertz, for example, means it oscillates 10 times in 1 second. Now here's a nice little animation that shows how a sine wave relates to the movement of a circle or an angular frequency. So you can notice in the diagram, when I go through one cycle of the sine wave, so here it looks like they're choosing the 3 o'clock position on the wheel to be our starting point. You can see that's when the graph is at the origin, and then it goes up to its maximum, down to its negative maximum, and back to the starting point. So one cycle of the sine wave oscillation corresponds to one rotation of the circle. So you know that there are 2 pi radians in one rotation of a circle. One time around a circle is 2 pi radians. So if I go through one complete cycle of the sine wave, I also go through one complete rotation of the circle, which is 2 pi radians. So we can describe the position on the sine wave by the position of the circle in radians. So radians in a full circle divided by the period is the radians per unit of time. So the ratio of the radians to the time. So I'll just use the time and the radians for one complete cycle. So in one complete cycle, I have 2 pi radians, and the time it takes for one cycle, by definition, is the period. So radians per unit of time is 2 pi radians per period. And since 1 over the period is the frequency, remember that frequency and period are related in that they are reciprocals of one another. I can replace 1 over t with f, and I see that my angular frequency of an oscillation is equal to 2 pi times the frequency. All right, on our next slide, we look at the equation that describes the sine graphs or the cosine graphs that we're looking at. Realize that we call it cosine, but because this is the way we've chosen to start the graph at maximum displacement, just like the cosine graph does. But really, a cosine graph is sinusoidal in nature. So you might hear me say sine curves or cosine curves. Just know that it's all sinusoidal, and we're talking about simple harmonic motion. Okay, so here's the equation for this graph. It has amplitude, it has angular frequency, and it has phase. So for a given wave or a given oscillation, those will be constants, and what's varying is time. This equation is the general form of a sinusoidal waveform, the general form of the equation for a sinusoidal waveform. So specifically for displacement, the amplitude is x max, the maximum displacement in the x direction. So its position x, or displacement x, as a function of time is equal to the maximum displacement times the cosine of omega t plus phi. We know that velocity is the derivative of displacement with respect to time. So down here, we've taken the derivative of this equation 15.3, and we know that the derivative of cosine is negative sine, and then we multiply it by the derivative with respect to time of what's inside the parentheses. So that would be omega. So our velocity equation then is negative omega x max times sine omega t plus phi. And to come up with the equation for acceleration, we take the derivative again with respect to time, and the derivative of sine is cosine, and multiply times the derivative of what's inside the parentheses changes this omega to omega squared. And we get our equation for acceleration as a function of time, negative omega squared x max cosine omega t plus phi. Later in the presentation, we'll show you an Excel spreadsheet that mathematically calculates these equations, stepping in increments of 0.001 seconds, and graphs them for us so that we can plug in numbers for x max, omega, and phi, and see what the corresponding displacement, velocity, and acceleration graphs look like. So here are the graphs again of position, velocity, and acceleration. And we know that the derivative of position is velocity, and the derivative of velocity is acceleration with respect to time. So you can use that to help you generate these graphs. You know that the first graph, the position graph, is just the cosine curve. So you can draw that from memory, hopefully. And then the slope, remember the derivative is the slope. So you can generate the velocity graph from the position graph by looking at the slope of the position graph. So here is a slope of 0. So my value of velocity is 0. Here my slope is 0. So my velocity is 0. And here my slope is 0. So my velocity is 0. And then in this region from 0 to pi, or 0 to 1/2 second, the slope is negative. And the slope is gradually increasing until this inflection point here, and then it decreases. So that's what we see here. The magnitude of the velocity increases, and then the magnitude of the velocity decreases back to 0. Same thing over here, except now it's a positive slope. The slope of the position is increasing to this inflection point, and then the slope is decreasing. So the value of velocity increases and then decreases back to 0. So all you had to do was generate 1, 2, 3 0 points on the velocity graph, and then look at the slope, and is it increasing or decreasing, and you can fill in the rest of this. If you want to know exactly what the magnitude of the, or the amplitude is of the velocity curve, then you have to remember this coefficient, okay? Which you can get by taking the derivative of this equation. Okay, and then the acceleration, you can generate that graph from the velocity in a similar fashion. You look at this point here and this point here. That's where the slopes is 0 of the velocity graph. So I have values of 0 for acceleration at those 2 points. And over here, my slope is negative, so my velocity values are negative. And in this region, my slope is positive, so my acceleration values are positive. And over here, the slope is negative, so down here, my acceleration values are also negative. Okay, here's the Excel file that I will share with you. I'll either put it on School Loop or Google Drive or something. I'll let you know where to find it so you can try it yourself. But here, I've set up a Excel file that graphs the equation x max times the cosine of omega t plus phi for displacement, and for velocity, my equation negative omega times x max times the sine of omega t plus phi, and down here the acceleration negative omega squared x max times the cosine of omega t plus phi. So you can see all the graphs, and here you can enter the amplitude, the frequency, and the phase shift now as a multiple of pi. So if I wanted a phase shift of pi, I would enter 1 here. So let's go ahead and just see how it changes if I change my amplitude to, say, 1.5. Okay, so you can see the amplitude of the wave changed to 1.5. I still have only 1 cycle per second, so my frequency is still 1. If I change that to 2, then you can see now in 1 second I have 2 cycles or 2 oscillations per second. And of course, if I change that to some other number, let's try 4. There you go. You see I get 4 oscillations in the 1 second time interval. Okay, so I'm going to put this back to 1. And here I let Excel calculate omega for me. Remember, omega is 2 pi times the frequency. So if I go back to a frequency of 1, then of course the number in here is 2 times pi. And if I put 2 in there, then it's 2 times pi, which is 4 times pi, or 12.56, and so on. So going back to a frequency of 4. Okay, now the phase shift. This is going to be the one that gives students the most difficulty in understanding. If I want to shift this graph from left to right or right to left, in other words, adjust where my starting point is, where I consider time t equal to 0 to be. Let's say I wanted this portion or this part of the oscillation to be my starting point. So I'm going to shift the phase to here. And so what fraction of a full cycle is that, right? One full cycle is 2 pi radians. So if I wanted to shift it to here, that's 1/4 of 2 pi, right? So that's pi over 2. So if I shift my starting point to here, that's a phase shift of pi over 2. But we have to look at which way do I shift it. Do I shift it to the right or do I shift it to the left? So if I shift my starting point, I'm going to add pi over 2. So let's do pi over 2 is 1/2. So 0.5 is a multiple of pi. There we go. And you see it shifted so that my 0 point changed to right there in the oscillation. Let me put it back to 0 so you can see that again. Okay? So I moved my starting point to right here, or I shifted it, a phase shift of 1/4 of a cycle. So if a cycle is 2 pi radians, 1/4 of a cycle is pi over 2. And so that's what I did here, 1/2 of pi, 0.5, and it's shifted to that spot. Okay? If I did a full or half a cycle, right? Half of 2 pi is 1 pi. And so you can see now my starting point shifted to right there. Notice that when I use a positive phase shift, the graph seems to shift to the left. So if I enter a positive phase shift, it looks like my graph shifts in the negative direction. The reason that is because I've shifted my starting point to the right, and when I then move that over to time t equals 0, it causes the whole graph to shift to the left. So let's put in a negative half of a 1/2 multiple of pi. In other words, a negative 1/4 of a full cycle, 1/4 of 2 pi. And when I enter that, you can see it looks like it shifted to the right by 1/4 of a complete cycle. Okay, so now what we're going to do is we're going to take our equation for displacement and we're going to take our equation for acceleration, and we see that in my equation for acceleration I have x max cosine omega t plus phi. Well, that's exactly up here what the displacement as a function of time is equal to. So I'm going to take this whole part of the equation for acceleration, and I'm going to replace x max cosine omega t with phi plus phi with xt. And so that's what I get when I do that. That says the acceleration at some point in time of my oscillation is proportional to the displacement. Okay? So whatever the displacement is, I multiply it by negative omega squared, and that is the acceleration at that same moment in time. This is the hallmark of simple harmonic motion. It's an extremely important equation, and it shows us that the acceleration and the displacement are proportional. Notice also this negative sign tells me that the acceleration has a sign that is opposite to the displacement. So if my spring is displaced in the positive direction, the direction of the acceleration will be in the negative direction, and vice versa. If I'm displaced in the negative direction, the acceleration will be in the positive direction. And you know that acceleration and the force that causes acceleration are always in the same direction. So that means the force is always in the opposite direction as the displacement. This is known as the restoring force. And whenever a spring or a pendulum is displaced from the equilibrium point, the force is always trying to push it back towards the equilibrium point. We call that the restoring force. And that shows up in the equation by the fact that the acceleration has the opposite sign of the displacement. All right, our next slide deals with section 15.3 from the book, the force law for simple harmonic motion. So we'll start off using the example of a mass oscillating on a spring. We know that the force is equal to mass times acceleration. That's Newton's second law. And so we'll take our equation for acceleration that we had from the previous slide that said acceleration as a function of time is equal to its displacement times omega squared times -1. And we'll replace A with what it's equal to, negative x omega squared. And I'll just regroup the variables and so that I have F is equal to negative m omega squared times x. Well, if we relate this to Hooke's law, we know that F force is equal to negative kx. So we look at these two equations and we see that m omega squared is k. All right? So knowing that k, the spring constant for the spring, is equal to the mass that's oscillating times omega squared, I can solve that for omega, and I get omega is equal to square root of k over m. And we know that omega is equal to 2 pi over the period, or 2 pi times the frequency. And so I can solve this equation now for the period, and that tells me that the period is equal to 2 pi times the square root of the oscillating mass over the k constant. So if I know the mass of the mass on the spring, and I know the k constant of the spring, I can calculate what the period of oscillation will be for that oscillating mass on the spring. All right, and here is my LHS Physics Taylor website. If you want to see an experiment that proves this equation for a period of oscillating spring, go here, quick links to videos on the left side. Click on that and scroll down to the last section that says Hooke's law, and right here, spring constant and oscillation period. You can click on that to watch a video of an experiment that shows that the period is equal to 2 pi times the square root of m over k. And also you can watch another video, if you like, from MIT professor Walter Lewin. He does a very good job of explaining a lot of this stuff.